Okay, in this video, am I going to say okay now all the time? In this video, we're going to introduce the fundamental theorem of calculus. Now, this fundamental theorem of calculus is so great, it's got two parts. We're going to start with the first part, do some examples, introduce the second part, and then do some examples, and that'll be the next 4 videos to finish off the section. So, yeah, without further ado, again, I told you I was not going to write fundamental theorem of calculus. It's too many letters. But FTC just means fundamental theorem of calculus. So here it is. FTC, part 1. Part 1. Okay, here we go. Let F be continuous. As a side note, a lot of this stuff doesn't require continuity, but things get a lot more fun when you don't have continuity. But a lot of these do work without continuity in various forms. So let's say we have a continuous function over some interval a to b with capital F being equal to the integral from a to x of f of t dt. Then we have something happen. But before I tell you what happens, I want you to look at this because this, I think, should look kind of weird. Most of the time when we have definite integrals, we have it go from a to b, from one number to another number. But here I'm saying this upper limit, these are called the limits of integration. The upper limit of integration can be anything. Anything. And then that, depending on what x is, maybe x will be 2 or 3 or 4 or 5, this definite integral will have a different area, will have a different value. So if it can be anything and have a different value, let's think of it as a function. That's all functions are, right? A rule that you give me an input and I give you an output. In this case, our function is an area function because definite integrals are just areas. And so this is the area depending on how far we go. Again, you don't have to necessarily write this down or this next part down, or you can write it off to the side, but I just want to talk about what we're dealing with before I get to the conclusion. Maybe let's look at a function. Maybe here's a. So this capital F, and again, this would be lowercase f here. This capital F is a function, and this capital F will give us the area at any point. So if this is our x, it gives us this area. But maybe we make x a little bigger. Then capital F gives us this area. All right, so whatever little x is, capital F is going to give us the area up to that point. And as a side note, I shouldn't have just erased it, so I won't. The magic of technology. As a side note, x can be over here. As long as the function's still continuous over here. And then remember, the integral from a to x going backwards. Remember, we had a property that we can go backwards. We can have the smaller number flipped, kind of. And then it just flips the limits of integration and adds a negative. We had a property for that. All right, so all right, now I'm going to erase it again. Let's finish. I know I left y'all on a cliffhanger. I'm sure you're at the edges of your seats going, Jason, what's the conclusion to the fundamental theorem of calculus? I gotta know. Maybe you paused the video and you Googled it yourself. You said, I can't wait. I need to know. Here it is. Then f prime of x. Ooh. Did you expect a derivative to come into play? Because here we've got one. If we have this function, which represents the area, depending on how far we go, we can say something about the derivative of this function. It's going to blow your mind. It's just equal to the integrand, the slope of some other function. Wow. So this is just kind of rephrasing what we've talked about before. The area under the derivative is just the net change of the original function. And we'll see that more in part 2 of this fundamental theorem of calculus. But in other words, it says that the area function is something called an antiderivative. Okay, and we haven't officially introduced that term yet. So this is definition part 2. F is an antiderivative, that's an A, of little f. That's a very important definition for this entire day. So again, just another way of rephrasing this, the area under the curve can be written as a definite integral, we know that. And the derivative of that area function is the integrand. So just another way of rephrasing kind of what we've talked about before. Fundamental theorem of calculus. It tells us also another way of taking the derivative of integrals, which also connects to antiderivatives. So again, just to unpack this definition a little bit more as well, the derivative of one function equaling another means that the antiderivative of that function is this one. Okay, derivative of f equaling g means the antiderivative of g equals f. Antiderivatives are basically inverses in a sense. They're not precisely inverses, but they're very similar, right? So again, if f prime of x, or let's write it a different way, right? If f prime equals some function g, then the antiderivative of g will equal f. Actually, I'm going to wait to write that down. There's a better way of doing it once we introduce some new notation, which we will do in video 4. We'll introduce that notation in video 4. I'm getting ahead of myself. There's a lot to say about antiderivatives, but we're going to wait on that. In the meantime, antiderivative is just basically the backwards of derivatives. So if the derivative of x squared is 2x, antiderivative, oh, I can write that down now, yeah. You know, the derivative of x squared equals 2x, then what we would say is x squared is an antiderivative of 2x. And in fact, there's infinitely many antiderivatives, but we'll get to that again later. So that's the relationship here. We'll draw a double-sided arrow. But again, I'm getting ahead of myself. We're just going to do a quick little proof. So I'm going to prove this guy won't be too hard. You could do it too. I'm hoping. I haven't recently proved this. I just kind of know the direction to go. So we'll see if I can do it. Proof. So we're trying to prove that this we're trying to prove that this equals that, sorry. The derivative of f prime equals f. So we're going to do it like we do most proofs and just start with the left-hand side. We want that the derivative, I'm going to write it over here just so we don't have to keep changing pages. This is what we want, so we're going to start with the left-hand side. And well, what is the derivative of f? Now, if you thought your limit definition of the derivative days were over, you thought wrong. So the derivative of a function is the limit as h goes to 0 of that function evaluated at f of x plus h, evaluated at x plus h, minus the function evaluated at x all over h. Remember, this is the slope of the secant line. H is just the difference between 2 points, and then we're finding the slope of the secant line between those 2 points. All right, so that's what we've got here. And now all that's left is plug things in and simplify and do a couple things. So the function, remember, that's the integral function, the area function from a to x. As a side note, we are using t here instead of x. X is very common, but we're using t here because we don't want two. If we have two variables that are different, they need to be differently named. We can't name them both x because we already have an x, and that x means something specific. So the inside variable, the variable of integration, can be anything except x, because we're already using that. We could have wrote f of s ds, f of y dy, f of z dz. All of those are good. T is very common. Okay, so let's factor out the h first. Limit as h goes to 0 of 1 over h times, again, if we factor out the h, this is what we're left over. What is the capital F evaluated at x plus h? And again, remember that f of x is defined to be the integral from a to x of f of t dt. So first we're evaluating that not at x, but at x plus h. So we replace all the x's with x plus h's of f of t dt. And then we're subtracting the function evaluated at x, which is literally this, integral from a to x of f of t dt, and we want to simplify. And we're hoping to eventually get here. Always, for any proof, always think about where you're trying to go. And that's where we're trying to go. So we're going to need to do some simplifying and eventually do some tricks. Well, right off the bat, we can combine these. We have a property for definite integrals. This first one is the area from a to x plus h. The second one is the area from a to x. So this is like a big area from a to x plus h. And the second one, right? The second one is only going up to x, is this area. So we take the white area and we subtract the red area. Well, what are we left? White minus red is going to be green. The area from x to x plus h. All right, so the picture here can really help, remembering definite integrals and thinking about them as areas. That's going to give us the limit as h goes to 0 of 1 over h times the integral from now x to x plus h of this function. Now remember, when we do limits, a lot of times, if something's continuous, we can use direct substitution. So you might think, oh, can I use direct substitution here? Well, if we use direct substitution, if we plug in h equals 0, then we're going to get like, I'll just write it over here and erase it because it's a little weird. I don't want to write it behind my head. Then we'd get 1 over 0 times the integral from x to x of this function. And remember that from x to x, right, from x to x, that's also 0. From any, if the limits of integration are the same, there's no area. That was another property we had. So this is a 0 over 0 situation. It's undefined. And now I'm hoping that you think, aha, Jason, I know what to do next. Let's use L'Hopital's rule, right? 0 over 0, and we have a limit. L'Hopital's rule is great for that. The problem is, the problem with L'Hopital's rule here is, to do it, we'd have to take the derivative of this function. And to take the derivative of this function, we have to use the fundamental theorem of calculus, which is what we're trying to prove. So in order to use L'Hopital's rule, we'd have to use what we're trying to prove, and that's not good proof technique. So I hope you thought it, but it won't work because we'd have to use what we're trying to prove, which is no good. All right, so that's what we have right here. Let's continue on the next page. See how we can simplify this, because this next step is really going to be the really kind of tricky one. Okay, so let's look at this. Remember that h is just the difference between the 2 points here that we're thinking of. H is just the size of the interval, right? Because really now what we're looking at is the The integral is just the area under this function from x to fx plus h. And h, right? H is just the width of the interval. So what is the area divided by the width? It's the average value. I told you it'd be coming back. Mean value theorem for integrals is coming back because this right here is the average value of f on the interval from x to x plus h. And it gets even more interesting here because this is the average value and we have a limit. What is the average value of a function? Don't think of anything super fancy, but what's the average value of a function as that interval gets infinitely tiny? If the function's continuous, right? Think about this point is always this point. And then we're making this interval smaller and smaller. So maybe we have an h here, and the h gets smaller, the h gets smaller. What's the average value as this red point gets closer and closer together? Well, if the function's continuous, eventually, that average value will just be f of x, which is exactly what we want to get to. We want to show that this left-hand side is equal to the right-hand side of just f of x. Okay, so what we're going to do is say, okay, f is continuous. So by the mean value theorem, this is the same as f of c. We know at least one c exists. Where c is in the interval from x to x plus h by mean value theorem, since f is continuous. And since we have a continuous function, as h goes to 0, that's the exact same thing as x going to c of this, which by the definition of continuity is exactly f of c, which is the right-hand side and exactly what we wanted to prove. These last few steps, I went through them quickly, but think about them and ask me if you have questions about it. And try to see if you can figure out exactly why these are indeed the same. Okay? And this picture is really what's going to get you there. And we just proved the fundamental theorem of calculus using the mean value theorem, which we didn't prove the mean value theorem. So the way that proofs normally work, right, is you got to prove everything leading up to what you're using. But I didn't think that was the mean value theorem was that instructional to go over for the proof. So we skipped that. But here it is. And that's this video. So no specific problems for this video. The next video is when we're going to go through a bunch of examples on how to use this mean value theorem. We'll do a lot of derivatives. We'll get to use the chain rule. So hopefully you're fresh on the chain rule. And yeah, should be good to go. You can start some of the problems early if you want. And then the next video will just be full of a bunch of examples to hopefully help.